Okay, here goes.
So, test 3. We're having tests the following 2 Thursdays. So test 3 is on July 10th. Test 4 is July 17th.
July 10th.
And the final will be the following Tuesday, which is July 22nd. Okay, so this is this Thursday, this week Thursday, this is next week Thursday, and the Tuesday after that. That's when the final is. So the final is 2 hours 15 minutes long. It would look 2 hours 15 minutes. So it would look pretty much like the finals that you see on the math department website. The format's going to be similar. Right. These two tests.
Is it the same class time?
Yeah, during class time, same class location as well. I think for July 21st, there shouldn't be anyone in class, so we could have a review session. Technically, we don't have class, but we might, if you guys are up for it, we can do like a review session. So, and then that review, final review. Monday, July 1st. Same time, same bad channel. Regular classroom, regular class time.
So it's still like half in the computer?
Yeah.
Okay. And do we know where the final is?
Here, in the class.
Oh,
so
it's
the
here,
final is
okay.
classroom, class time.
Oh, okay.
Right. Because our class time runs 2 hours and 20 minutes, so we'll cover that. I'll think about what I was taking.
Oh, please make your take home. Wait, all in favor of the take home, raise your hand.
Also, those computers are so slow.
They're so
If
slow,
somebody
it's
gets a
gonna take
computer
us.
that's slower than the other person, that's unfair.
Well, if we all use it at the same time, it's going to crash. Like, you know
You
how
have to actually time each computer and then adjust the amount of time allowed for each person based on that.
I don't know. It'll probably take on, because we probably don't have enough computers for 1 person at a time.
There you go.
Oh,
whoa.
Just have to make it super hard then.
Well,
But
yeah,
basically what we
that's
want
right.
is MATLAB. So at the end of the day, you can really use MATLAB to do almost anything we've been doing. MATLAB could do double integrals, triple integrals, it can do partial integration for you, can find maximums and minimums, can do all that. But really what we've been focusing on is the visualization aspect, right? Drawing vector curves, surfaces, things like that. So that's the sort of stuff I'm going to test you on. Maybe I might do a bonus problem with all those other analytical stuff, but really, if you know how to do all the visual stuff we've been doing, that you should be fine.
So that's just from the MATLAB notes sections?
Yeah, from the
whichever
MATLAB
sections
notes,
we
the stuff we've covered.
whatever.
Okay, so we're going to continue now with 13.6. We're backtracking a little bit. I forgot to do this. It's not again, not a lot. It's going to be like 12.4.
Okay, don't
Yeah.
blink.
Don't blink.
Yeah.
How much is the MATLAB final contour? Is it a portion of the MATLAB grade, or?
It's like
Yeah, it's still under the MATLAB grade, but it will be worth somewhere between 5 and 10 homeworks.
Oh, wow.
Yeah, so I think I was grading each MATLAB homework out of 10 points, and then I'll probably make this some between 50 and 100 points.
Yeah, we never got back any of the MATLAB homeworks.
Are those grades also on the Jupyter?
They're not that. Okay.
Tell the other minion that this minion is gonna come after it.
The minion uprising.
That extra 5% will really
Help us.
I have to like promise you guys we're going to conquer the moon so that you're all getting to
Do you want $1?
Okay, so in 13.6 there's a lot of stuff going on, but we're really good. It's not even, I don't think it's even called surface area, but we'll only need surface area from that. Alright, so you do a lot of stuff talking about how to parameterize different surfaces and things like that, and they sort of tell you how they derive this formula, but I'm not even going to tell you, I'm just going to tell you the formula. That's basically what we're going to use from 13.6, and that's pretty much it. But they'll tell you how they derive this formula. The more sophisticated ways to find the magnitude of the normal vector to the surface. And in 392 you'll see how that works. You could also sort of generalize the calc2 argument for the arc length and find the surface of rotation, and you could get to the formula that way as well.
Isn't it true like cross product being equal to the magnitude of the cross product being equal to the area of a parallelogram? And
Yeah. So pretty much, yeah, that's the magnitude of the normal. Right. The normal would be the cross product. So you sort of think of a surface, like if you have a surface here, you think of it as in patches, right? And then the cross product at that point will give you the area
of the little parallelogram.
The little parallelogram patches. And sort of, and the integration sort of adds them all up. Yeah. But you don't really need to know that. You just need to know the formula and use it. But that's sort of how it was derived. Yes. An example. Let's start with that one first. I have another example, but let's start with that one. Okay, so we can actually draw a picture here. With the cylinder x squared plus y squared equals 9. So this would be 3, this would be 3. And now we want the part of this plane, and we can graph the plane. It cuts through z at 10. And x x it would cut through at 5, and y it would cut through at 2. So it actually goes below the xz and over. So I actually want to find this surface area of this guy. Alright, so I'm inside a cylinder, there's a slanted plane cutting across this thing. And I want to find the area of that part. So it sort of looks like this elliptical thing in space. Now we do that by area is equal to the integral over d of the radical partial with respect to x squared plus the partial with respect to y squared plus 1 dA. Here fxy is so is that 10 minus 2x minus 5y, which means partial with respect to x is minus 2, partial with respect to y is minus 5. This means that your area is just double integral of the radical of 2 squared plus 5 squared plus 1. This is just the radical 25 plus 5, that's 30. Now how would we set up our region of integration here? What does D look like?
Wouldn't that be the projection of the plane?
Yeah.
So it'd be a circle.
What's the radius?
3.
Okay, what's a great way to set up this circle? Polar. So if you wanted to do polar, what's r and what's theta?
R goes between 0 and 3,
0.
and theta is 0 and 2 pi.
0 to 2 pi, 0 to 3, r d theta. Alright, but this is just a constant. This is just radical 30 times double integral 0 to 2 pi, 0 to 3,
R d theta.
r d theta. Now you could also notice that this is actually radical 30 times the double integral over d of the function 1. In which case, you know that that double integral is going to give you actually the area of this circle.
No.
So it's going to be radical 30 times pi r squared. So it's 9 radical 30 pi. Now if you had done the long way, r squared over 2, plug in all limits and blah, 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 you would have gotten here anyway, but you can notice that it was just a constant. So we gave you the area of the region. Example.
So whenever we see a double integral of 1 dA, if we are given constants, can we just take the area?
Yes, it's going to be the area of the region. Now, as long as
Right.
it's a region that you know how to find the area of, it's a rectangle or a circle or something, triangle or something easy, yeah, you can literally just find the area.
Okay.
Yeah. Find the area of the part of y equals x squared plus z squared. To the right of the Okay, try to set that up. Oh, and by the way, the practice problems for the third test are already on the website, so you should be able to see them. Okay? You know how to set it up? You did it. Huh?
I know how to draw it.
That's a start. Oh, how do you draw it?
So notice that it's a paraboloid that opens up on the positive side of the y-axis.
Alright, so it's opening like that.
And it's basically the space that's between the xz plane and the plane y equals 1.
Right, now it's important to know that this is hollow. Right? This is, I just want the skin. Right? So this is,
So whenever we see surface area, we
yeah, it's
should
always a
think the
two-dimensional
shell.
thing. The shell,
Okay.
the outer skin of the thing.
Right.
Right. Because area is a 2D property. Right, so it's really, we want the area of this whole thing. Now, region of projection, probably the easiest way is to go with projecting here
In the XZ plane,
in the XZ plane.
it's a circle,
That's going to be a circle
radius 1.
of radius 1, because that intersects where y equals 1.
You just need the right side of that system.
Yes, which is over here. So this is going to be x squared plus z.
We wouldn't know that either way though, no?
Huh?
That it's on the right side of that Z-plane.
Yeah. I just read it that way because I wanted to get you used to the language. There are several questions in the homework where they say that, like, so it's on the left side, or it's in front, or it's behind. So you should know. when they say make these sort of descriptions, right or in front or behind, they're assuming that you're setting up the axes exactly this way. X here, Y here, Z here. If you draw your axes a different way, then it's gonna sort of mess you up. The book assumes that your standard way of drawing the axes is this. So to the right means here's the XY plane, you're literally to the right. Okay. So what does the integral setup here look like?
Well, wouldn't it be easier to do this in polar coordinates?
Sure, but I need to find this part. What's this going to look like?
So that would be 2x plus 2z squared plus,
No, you need to write it as a function of
I
x
meant-
and y.
oh, right.
No, you don't.
No.
It can't be F and Z.
You could write it as a function of x and z,
Yeah.
which I could let be x squared plus z squared. I can find the partial with respect to x,
2x.
partial with respect to z, and then use the area is the double integral over d of fx squared plus fz squared plus 1 dA. Where now I know my dA is in the xz plane. So it's pretty flexible here. The x and y, they're really just dummy variables. You write it in your function as a function of two variables in any plane. You can make this work. Just swap out the guys that you don't want. Right? So now a would be double integral over d of the radical of 4x squared plus 4z squared plus 1 dA. Now how would you set up the limits here? Which again,
It's a
in this
circle,
case, we have a
radius
circle
1.
with radius 1.
So r goes
And we're in
from
x.
0 to 1, and theta would go from 0 to 2 pi. And then you would have the square root of r squared plus 1.
4r.
4r
So
squared.
4r squared plus 1. Thank you.
R dr dθ. Okay, and that's it. Now we evaluate. And we can't really use the area thing to help us this time because we're not integrating the function 1. We're going to have to actually go through this.
If it were just r squared,
No.
no.
So
Yeah, because
it
it's
would
still
have to
got
just be an
plus
R
1.
and we could do it.
Okay.
So here, there are no thetas represented here or on the limit, so I could actually evaluate the theta first and then get 2 pi. So it's just 2 pi times the integral from 0 to 1. 4r squared plus 1. dx. And then here you can do a u substitution if you want. You can do u is equal to 4r squared plus 1, du be 8r dr. So you put a 1/8 on the outside. Could also change my limits. When r is 0, use 1. When r is 1, use 5. And so that's the same guy. So now, That's our area. That's it for 13.6. Really, that's all the only application we care about at this point. Those of you going on to vector calculus, you're going to revisit 13.6 and do everything else in there. But in Calc 3, that's all we care about at this point. Going to be 12.6 now. Triple integral in what we call cylindrical coordinates. Now, all cylindrical coordinates really means is just polar coordinates, but we throw a third variable in there and we use triple integral. That's pretty much it. Standard way is to use z as the other variable. All this means is just in one plane you're using polar coordinates to locate your point, while in the other plane is just the regular rectangular coordinate. So for example, I can locate a random point here in space floating above the xy plane somewhere by, if I know where it's projecting right down to the xy plane, I can connect that with a line. I can move by an angle theta, extend from the origin by a distance r, and then rise by a distance z. And then I can locate this point by the coordinates r, theta, z. Right? So you tell me the r, how far it is from the origin in the xy plane, the angle I have to move, and then how high I have to jump. I can get to the point that way. Right? So it's really like rectangular coordinates, except your x and y are replaced by polar coordinates. Right? And as the name suggests, cylindrical coordinates, it's really useful most useful if the solid of integration is a part of a cylinder. That's why it's called cylindrical coordinates, right? So if you're integrating over a cylinder or part of it, cylindrical coordinates is a good thing for you to try. Just like how if you know you're integrating over part of a circle in the xy plane, polar coordinates is a good thing to try, right? But that's how we know when we want to use it. Before I move on to integration though, let's talk about actually looking at surfaces in this new mindset. my notes I had left off the name. I should have asked you guys what those guys are. Whatever. Rewrite the equations for those surfaces in polar coordinates. Okay, how would you write these in polar coordinates?
R squared is 16.
This one? This one?
Is equal to R.
This one?
Squared plus d squared equals 1.
Alright. So when you're thinking in cylindrical coordinates, if you see R, it's really a cone. Right? If you see R squared, it's really a parabola. Right? Things look, they look different, but it's really, you're just swapping out the x surface y squared for R squared, etc. So, cylindrical. And finally, as far as integration is concerned, this is really what you need to know. You can represent a triple integral over cos e of x, y, z, dv as something to b. Theta to dt of theta. F of cosine theta or sine theta. So basically, that's what cylindrical coordinates says to transform your integrals, right? Everywhere you see an x, you replace with r cosine theta. Everywhere you see a y, with r sine theta. Your polar coordinates limits come out here. This is your dr d theta. You also have a dz here. Right, so that's where the triple integral. The z doesn't change. And But again, in triple coordinates, these things, they're really flexible. So if you want to project the polar coordinates into another plane, you could, right? So for example, in the YZ plane, you could have done it, just let Y be let Y and Z do the polar, and X be itself, and then you'd have R dx dRd theta, right? You can use any word that's convenient, right? If your projection is a circle in some plane, you can let that plane cover the polar coordinates part, and then the other variable cover everything else. We can jump to examples. I won't finish all the examples. Example. Okay, what does that solid look like?
Circular cylinder.
Circular cylinder.
And z equals 0 and 5.
Goes up to z equals 5, down to z equals 0. And this is the cylinder x squared plus y squared equals 9. It's a circular cylinder. The solid is cylindrical, which means it's really nice to use cylindrical coordinates here, especially since I see an x squared plus y squared. It means I'm going to want to keep the circle in the xy plane. So I'm going to do polar in the xy plane. And hopefully it will help me with this because I can actually integrate e to the x squared or e to the y squared. So polar is going to really come in handy there. So here, limits. I'm going to do r, theta, and z. R would go from 0 to 3 because the circular radius is 3. Theta goes from 0 to 2 pi, it's the whole cylinder. And z goes from
0 to 5.
0 to 5, right? They're flat planes. And so now where I see x, remember I replace with r cosine theta, y replace with r sine theta, so x squared plus y squared is r squared. And then I have r dz dr d theta. So if I do that, that's just going to give me 5, 0, 2 pi, 0, 3, e to the r squared r. Because integrate this with respect to z first, I just get a z here. Fundamental theorem of calculus, plug in the 5, minus you plug in the 0. So I just get 5 of this. If I integrate r squared e to the r squared, I get 5 over 2, 0 to 2 pi e to the r squared. Between 0 and 3, theta. Times 2 Another example. What is this guy equal to? What's the region of projection?
Circle radius 1.
So your x goes from -1 up to 1. Your y goes from the positive radical 1 minus x squared to the negative radical 1 minus x squared. Right? This you can rewrite as x squared plus y squared equals 1. And you want both the top and the bottom. So it's actually a whole circle of radius 1, which means the two outer integrals could be replaced by 0 to 2 pi, 0 to 1. What about the inner integral?
0 to 2.
R squared up to 2 minus r squared, right? Everywhere you see x replaced with r cosine theta and r sine theta. X squared plus y squared is r squared, which means this becomes what?
R squared.
Right, r squared to the 3 over 2, the 2's would cancel, so that's just r cubed. And then this is your dv, that becomes r dz dr d theta. Now, okay, so it's just the value. So z integrated with respect to z. Just get z, and then plug this in. So it's r to the 4th times 2 minus r squared minus r squared. So that's just 2 times 2 pi from the outer integral times r to the 4th minus r to the 6th. Times this is r to the 5th over 5 minus r to the 7 over 7 means 0, 1. Yep.
I think you might have put it on the 1/4.
Where?
When you multiply, so r cubed, when you integrate r cubed times r, oh no, you're integrating with respect to z further.
Yep.
My bad.
Yes, with respect to z. So I just have a z popping up here, and then I plug in the 2 minus r squared minus the r squared, and that gave me this. Okay. And so this is just 1/5 minus 1/7, which is just 7 over 35, 2 over 35. 8 pi over 35. Quick question. What if I had done something like...
It's just a semicircle, so that would just be half of it, right?
Would it be half? How would you set up the limits?
Okay, so it'd be 0 to pi.
No, it's gonna be
Would it be 0 to pi? No.
Just second.
What region would this be described with?
0 to pi by 2.
X going from 0 to
X would be
Right,
0.
you have the full circle, but you only want x from 0 to 1, which means you're only taking the right part of the semicircle.
Okay, so 3 pi over 2. Or
No, it would be from negative pi over 2 to pi over 2.
You could do it that way, minus pi over 2 to pi over 2.
Or 3 pi to 5 pi over 2.
3 pi over 2 to 5 pi over 2 could also work. Yes.
Okay.
Right, so, and what if I did this?
Then you only have the,
Then I'd only have this part,
Okay.
in which my theta would be,
0 to pi over 2.
right, so little things like that can drastically change your limit, so always be careful. Always draw. Pay very close attention. Don't just see, oh, it's radical of 1 minus r squared, it's a full circle, 0 to 2 pi. It's not always that simple. Okay, how about this one? What's this?
It's top half of a circle.
It's a cone. And what's that?
Sphere.
Okay, so
you have a cone equals the ice cream.
looks like an ice cream cone. Yes. So this is a cone, the top half of the cone going up, and then you have that sphere. What's so funny? It is an ice cream.
Cross product. Cross product.
How do you find the normal line? How do you find the normal diagonal?
It's parallel. It's 0.
No guessing. Okay. So I really want you to find the volume of this ice cream cone.
Vanilla.
Vanilla. It's definitely rum and raisin. Okay. How do we find the volume?
We fill it with ice cream and put it on the scale.
Let's say I want to use with a triple integral, right? So the volume would be,
Do a projection of the circle down at the bottom.
it's the triple integral function of 1 dv, right? Of this thing. So you project, yes, you project this,
Down there.
and you get a circle.
Radius 1.
What will be the radius?
Radius 1.
Couldn't be radius 1,
Wait.
because the whole sphere is of radius 1,
Oh, right. It's 1 over root 2.
right? So it's this whole thing.
So it's 1 over root 2.
Yeah, notice that the intersection,
Right.
is
And negative 1 over
z squared equals x squared plus y squared. You plug it in here, you get 2x squared plus y squared. So you get x squared plus y squared is equal to 1/2. And so we could let r go between 0 and 1 over radical 2. Theta goes between 0 and 2 pi. What would z go between?
0 and 1. No. Between x squared and y squared minus 1.
What? Nope. Where would 0 and r be? That would be below here. Everything under the ice cream cone.
Z will be
0 to the
1 minus.
Right? If there's a little man trapped inside the ice cream cone, where's the floor?
Oh, use the function.
The floor is actually the cone, right?
Oh.
So the bottom is actually the cone, which has this equation. But what's the radical of 1x squared plus y squared? It's just r. The roof would be the sphere, the dome. So that's the top, which is
R squared plus minus 1.
this is
1
the,
minus R squared.
Sphere.
right. So you solve for z here, you get plus or minus the radical of 1 minus x squared minus y squared. This is just the square root because we want the top half of 1 minus r squared. And so in this case, the volume would be given by 0 to 2 pi, 0 to 1 over radical of 2, and this would be r up to the radical of 1 minus r squared. This would be r dz dr dz. And here with respect to z first, you just get z, you plug in this guy, so you have r times the radical of 1 minus r squared minus r squared.
Y minus R squared.
Huh?
Y minus R squared.
Because this r is there.
But you put it in the beginning, didn't you?
I integrate with respect to z, so I get zr, right? Then
Right.
from the integral calc, plug this into the z, so I have r times this,
Okay.
minus this into the z, r times r,
Oh,
r squared.
okay.
And so this you can use as substitution, right? That's going to actually give you what? So it would be 1 minus r squared to 0 to 2. It's going to be minus a half. No, just be minus. Minus a third. Right?
1 minus r squared.
So this would be r cubed over 3 to 0 and 1 over radical of 2.
What did you do with the
And
original
all of
R
this
outside of the...
times 2 pi.
What did you do with the R
Huh?
that was outside of the radical?
You can do substitution, you get this.
Oh, okay.
And so this would be 2 pi times minus a third, 1 over radical of 2, so this is 1 minus a half, so 3 over 2 minus that's going to look nasty. Okay. So it's 1 over 2 to the 3 halves times 3 plus a third. Bring in whatever that is.
Whatever that is.
Simplify. And you had a couple more examples here about changing coordinates, but I think you guys know how to do that. 'Cause, you know, from polar coordinates, you could have tangent theta is y over x and all that stuff. You guys remember that? So we'll stop there. That's actually 12.6.